Hey everybody, this is Mr. Malm, and this lesson is on the goodness of fit test, or the chi-squared test, and that's kind of a bigger X. It's the Greek symbol chi. All right, so here we go. And the chi-squared is used when you're doing more than one z-test procedure. When you're doing several at once, that's when you do the chi-squared. So the chi-squared test, or goodness of fit, allows us to compare two or more population proportions. So if it's more than two, then I would definitely do the chi-squared, and it'll tell you on the AP test. Our main goal here is to measure how well the observed counts fit the expected counts, okay? And the procedure is observed minus the expected divided by the expected. All right, we'll have three examples coming up. The sum is called the chi-squared and is labeled, that's the Greek symbol chi. And it kind of has a little hook to it. I'll show you in class, but chi-squared. Okay, the chi-squared family of distributions is used to assess the evidence against HO by the value of P that you get out of your chi-squared number using table E, which is in the back of the book. And your degrees of freedom also are n minus 1. So here's an example. The grain of America, this is example 13.1. So in recent years, the expression, the grain of America, has been used to refer to the belief that with better medicine and healthier lifestyles, people are living longer, and consequently a larger percentage of population is of retirement age. So we want to investigate whether this percentage is accurate. So the distribution of the U.S. population in 1980 is shown in the next table. We want to determine if the distribution of the age groups in the United States in 1996 has changed significantly from the 1980 distribution. So we'll test the following hypotheses. So your null hypothesis is the age group in 1996 is the same. There is no change. Remember, null hypothesis is always no change, the same as 1980. And the alternative is that it's different from 1980, okay? So here is the 1980 populations right here, okay? So from 0 to 24, it totaled all of these guys right here, and these are in thousands, so you can add 3 zeros to this right here, okay? So this is actually 226 million. All right, so if I did 93,777 divided by 226,546, we get 41% right here, okay? And then 25 to 44 is 27%, and so on and so on. And this should add up to 100% all the time, okay? So those are that's where we're going to get our expected counts, you guys. Okay, so we can also state the hypotheses in terms of the proportion of the U.S. populations that falls into each age category. Okay, so this means there's no change. Okay, so the population in 1996 is going to have the same percentages, 41.39, and then from this age is going to be 27.68, and so on. They're all the same. There's no changes. And so the alternative is at least one of them is different from the stated values. Okay, so let's begin. So the idea of testing this is we're going to compare the observed counts for the sample from the 1996 population with the counts that we would expect. So we're going to use those percentages that we just saw to get our expected counts. Okay, so the 1980 distribution is called our population, and the more the observed counts differ from the expected counts, and the more the evidence we have to reject HO, right? That should be familiar. So here's a random sample of 500 U.S. residents in 1996 that's selected at the age of each age group recorded here. Sorry, tongue twist. And the counts and percentages in each group are in this table right here. All right, so this is the observed for the 1996. These are my O's. These are my observed. So my O's are these numbers right here. All right, so we're going to go ahead and calculate. We're going to come back to this right here. So it's out of 500 people. We're going to calculate our chi-squared. So before we proceed, it's always a good idea to plot the data. In this case, a segment bar graph allows you to compare the segments of the population. So here's the segment bar graph. Well, they look pretty darn similar. So you know, I'm kind of wondering how different they are, although these guys look different right here. All right, let's see, I forgot to shut off my email. The next step is the test to calculate the expected counts for each age category. So in the age groups of the 1980s, it has not changed, and we're going to use those same percentages, the 41.39%. So we're going to multiply 0.4139 times 500, and that'll give us the expected counts. Okay, and then 0.2768 times 500, and so forth. That'll give us the expected count. So that's where I get these ones right here. Okay, so this was the 1980 percentages right here. So I just multiplied this percentage times 500, and that gave me the expected counts right here. Remember, the observed counts are in the other table right there, 13.2, table 13.2. These are the expected counts, so these are my E's right here. All right, so remember, this is my formula. O minus E squared divided by E. This will get me my chi-squared right here. All right, so so the sum of it is labeled chi-squared. Okay, so a summary of the calculations is shown in table 13.4. And the sums of the observed in the last column is 8.2275. And you're thinking, what the heck does that mean? I'll show you guys. We're going to use table E to describe this, you guys. The larger the difference between the observed and the expected, the larger the chi-squared will be, and the more evidence there's going to be against HO. All right, so here we go. Okay, so the observed, this was from table, I think, 13.2. These were the actual numbers that was given in 1996 out of the 500 people. And these were the expected. I multiplied the percentages times 500, times 500, times 500, times 500. So right here, this would be O minus E, so 177 minus 207, and then divided by E, divided by 207. I'm sorry, O minus E squared. I got to square it. So that's where this came from, the 4.3478. 177 minus 207 squared, and then divided by 207 again. Okay, and did that for each one of those right there. Don't worry, I'll show you how to do that in the calculator there. That's just all the tables put together right there. Okay, so in the chi-squared family distributions, the curve is used to assess the evidence against HO in the chi-squared. So the members of the family that is used is determined by the degrees of freedom. Since we're working with percentages, 3 of the 4 percentages are free to vary, but the 4th is not, because they have to add up to the 100%. So in this case, we're going to use our there's 4 different categories, you guys, so 4 different age groups, so 4 minus 1 is 3 degrees of freedom. Okay, so let's go turn to the back of the book and look for table E. I think everybody has table E. And the chi-squared distributions gives you the critical values, and it shows the typical chi-squared curve with the right-tailed area. So the chi-squared test statistics is pointed on the horizontal axes, and so here is I think I have that coming up right here. So in table E, so we're looking for a p-value of 5%, and degrees of freedom is 3, so we find that the critical is 7.81. Okay, because if it's not stated, then we always assume the 5%. So that's why we're looking at the 5%. So look in table E at the 5%. Okay, I'm looking at table E at the 5% right there, and I'm looking for 3 degrees of freedom, and I'm looking right now. See, I got my book open just like you should, and it's 7.81. And since your chi-squared is 8.2275 is more, that's extreme. So we can say that the probability of observing a result as extreme as the one we actually observed by chance alone it has to be less than 5%. So that gives us sufficient evidence to reject HO and conclude that the population is significantly different in 1996 than it was in 1980 at the 5% level. Okay, so here's a chi-squared density curve. It takes on only positive values and is always skewed to the right. The total area under the curve is 1. Okay, and it doesn't go out, 3 standard deviations or anything. It goes out to big numbers, you guys, because chi-squared, that last one we got was 0.822 or 8.22. And so as your degrees of freedom increase, the curve becomes more like a normal curve. And so see, here's the figure right here. It's skewed to the right. See how all these are skewed to the right? But as your degrees of freedom increase, which means your sample sizes are increasing, and it's getting more normal. Okay? So, goodness of fit test. All right, so to test the hypotheses of the distribution within outcomes, your null hypotheses is always your actual population proportions equal the hypothesized proportions. Okay, and your alternative is that they don't equal, that they're different from the hypotheses, and then we're going to calculate the chi-squared. Okay, and then we look it up on our table E for the p-value, all right, like we just did. You had to have your book open to understand that. If you didn't, then please go back and check that out. All right, so the conditions, you guys. All expected counts have to be greater than or equal to 1. Okay, no more than 20% of the expected counts are less than 5. All right, and genetics is the main field when using the chi-squared. Okay, so red-eyed fruit flies, and so we're going to see example 13.2 on page 733. Biologists wish to mate 2 fruit flies having genetic makeups, capital R, little r, capital C, little c, that indicate that it has one dominant gene R and one recessive gene small r. And for eye color, And then for the wings, it has one dominant C and one recessive lowercase c gene for the wing type. Each offspring will receive one gene from each of the two traits from both parents. So the following table is called the Punnett, I think it's Punnett or Punnett square, showed the possible combinations of genes received by the offspring. All right, so here's the parents. You can have these capital R, lowercase r, capital R, capital C, capital R, capital C. So the baby would have capital R, capital C, and so on right here. So you can just kind of see there's going to be 16 different types right there. All right, so there's my chart right there. And so any offspring that receives an R gene will have red eyes. And any offspring that receives a capital C gene will have straight wings. So capital R means red eyes, capital C means straight wings. So based on the Punnett square, the biologists predict a ratio of 9 of these will have red eye, straight wings. So here's red eye, straight wings, capital R, capital C. There's another red eye, straight wing. And they labeled them by X. So there's 9 X's that have a capital R and a capital C. Okay, and then 3 red-eye curly wings. Those are the ones with the Y's. 3 wide-eyed straight wings, and then 1 wide-eye curly wing. Okay, and so that would be the W. So there's that 1 W. And so if you look at these, so in order to test their hypotheses, the distribution of the biologists mating the fruit flies, so what there is, so if you did 9 out of 16, that's going to be the percentage of 9/16 will be the percentage that will get the capital R, that will get this X number right here. Okay, not an X number, the X lowercase letter, capital R, capital C. So of 200 offspring, they found, so these are the observed, 101 had red eyes and straight wings, 42 had red eyes and curly wings, 49 had wide eyes and straight wings, and 10 had wide eyes and curly wings. These are my observed counts. So do these data differ from what the biologists have predicted? All right, so step 1, identify the population. So the biologists are interested in the proportion of offsprings that fall into each genetic category for the populations of all fruit flies that will result from crossing 2 parents with genetic makeups RR and CC, capital R, lowercase r, capital C, lowercase c. All right, so their hypotheses are that there's no change, that they're going to equal. So this is my 9/16 right here, okay? And this was the other 16ths. I forgot how many there were. And this was the other 16ths. And this was the 1/16. I remember that one, okay? And so the null hypothesis is there's at least one of these proportions that's not the same. All right, and so there's my chart right there, and I'm going to stop it right here. Please go on to part 2 of this because I'm going to run out of time. It's going to cut me off. So check out video part 2.